Hi friends, welcome to VTeach. In this session, I would like to explain you about infinite impulse response filters. Simply, you can call it as IIR, infinite impulse response. Before going into the details of IIR filters, primary classification of digital filters. So they are classified as IIR, FIR. This is finite, this is infinite. Impulse response. Okay. So in this particular session, we are going to look into unit 3 of digital signal processing, which is about IIR filters. And then unit 4 is about FIR filters, finite impulse response filters. Now, basically, what is a filter? Filter is any particular device which allows particular frequency components and which rejects some other frequency components. Based on the allowing and rejecting of different frequencies, they are classified as low pass filter, high pass filter, band pass filter and band reject filter. And you very well know what is the difference. Which allows low frequencies, it is known as low pass filter. If the filter allows high frequency components, then it is called as high pass filter. And if the filter allows a particular range between two frequency levels, then it is called as band pass. And if the filter rejects that particular range between two frequencies, then it is called as band reject. So these are the four classifications. Now in this session, IIR filter design. Initially, the point what you need to remember is IIR design is called as indirect approach or indirect design. I'll tell you the reason why this is known as indirect method. Actually, here you need to remember two notations called as H of S and H of Z. H of S is analog filter transfer function and H of Z is a digital filter transfer function. In IIR approach, directly you cannot design H of Z. Initially you need to design analog function H of S, and this H of S can be converted into H of Z. That's the reason why this is called as indirect approach. So for designing analog filter function, there are two methods, and the names of those two methods are Butterworth approximation method and Chebyshev approximation method. Before going into this Butterworth and Chebyshev approximation method, here are few points like what are the advantages of digital filters over analog filters, and then what are the drawbacks of digital filters. Please try to go through these points, like there won't be any lagging or aging, then it is immune to noise. Analog filter, they are not immune to noise, but digital filter, they are highly immune to noise, and we don't have any problem with impedance matching. Like this, there are few advantages, and likewise we have a drawback called as quantization error. Please try to remember these points. Then coming to analog filter design methods, H of S design methods. As I told you, there are two methods. One is Butterworth method and second one is Chebyshev method. And here, before going into the details of these two methods, I would like to bring out a difference between two terms called as, and this is known as omega. This is also known as omega. Both are spelled as omega, but this is analog frequency and this is digital frequency. A very important point to be remembered. Both are frequencies, but this is analog frequency, this is digital frequency. Now coming to this analog approximation methods, the Butterworth approximation method, see what are the points to be remembered here. We are starting initially with an equation of magnitude. That magnitude equation is like this. The equation is given like this. In this equation, we have a term called as n, and this n is nothing but the order of the filter. It can be 1, it can be 2, it can be 3, any number, the order of the filter. And how to determine the order of the filter? There is an expression. We will look into the problem, and from that problem how to find n, we will be knowing it very easily. This is the expression for n. And see the transfer function or the transfer curve of this, that is frequency versus magnitude. It's like this. It is going like this, and up to this frequency it is pass band, and after this frequency it is stop band. So this is for low pass filter. It is allowing low frequencies. This is low frequencies, and high frequencies are getting attenuated. Okay, and here what is this sigma and what is this lambda? So it is allowable pass band and allowable stop band. Please try to remember those two terms for numericals. And we have even this alpha p and alpha s, that is attenuations in pass band and attenuation in stop band. And of course, see the relation between these two terms, sigma and alpha p, lambda and alpha s. These are the equations what you need to remember. Then omega suffix c, initial in this formula also we have that, omega by omega c. Omega is analog frequency and omega c is also analog frequency. Since c is there in suffix, you call that one as cutoff frequency. Omega c is cutoff frequency, and the formula for determining the cutoff frequency is clearly mentioned here, either pass band frequency by this thing. And if you want to determine the cutoff frequency, you should know about this capital N value, that is the order of the filter. That's why this is interdependent. Initially you are going to find capital N, and there itself if you do a mistake, then omega c will be a mistake and your entire problem be a mistake. Then in the transfer function of h of s, wherever s is there, replace that s with s by omega c after finding omega c. Okay, now as I told you, after finding the value of n, at least try to remember up to n equal to 4. If n equal to 1, the denominator is s plus 1. If n equal to 2, the denominator is this. If n equal to 3, the denominator is this. If n equal to 4, the denominator is this. At least you try to remember up to n equal to 4. In examinations, maximum the n value will be 2 or 3. That's it. Right. Now look into this problem here. This is problem 1 using Butterworth approximation method, and see 0.9 less than or equal to magnitude less than or equal to 1 up to 0.2 pi, and it is less than or equal to from 0.4 to pi. So from 0.4 to pi is this one, stop band, and up to 0.2 pi it is pass band. Okay, so try to write down the given data clearly first here. So here we got this 0.2 pi, omega suffix s is 0.4 pi, that is pass band frequency, it is 0.2 pi, stop band frequency starts from 0.4 pi. Okay, now see this, as per these formulas already I have shown you in this diagram. These are two formulas, or I have shown you here also two formulas. Based on that formulas, just check here, 1 by 1 plus sigma square, you are getting 0.9. Why? Because it is given as 0.9, and that 0.9 is nothing but alpha suffix p, pass band attenuation. So if you equal to that, you will get sigma as 0.4843. Similarly, 1 by 1 plus lambda square under root, equal it to alpha suffix s, stop band, then you will get lambda value. After finding lambda and sigma value, you know how to find the n value from this formula. Now n value you are getting 3.34. So 3 point anything, 1, 3.2, 3 point anything, whatever it is, you round it off to the next integer. It doesn't mean that if it is less than 3.5, let us take 3. If it is greater than 3.5, let us take 4. It's not like that. 3 point any value, you round it off to the next integer as 4. If it is 2.1, round it off to the next integer 3. So that's why n greater than or equal to. Okay, so since n equal to 4, you know what is the denominator. See this is the denominator. If you remember this, for n equal to 4, that is the denominator. So let me put the denominator, h of s expression is there. Now in h of x expression, we need to replace s by omega c. Now find omega c from the formula. This is the formula for omega c, cutoff frequency. So from this formula, if you find omega c, that value is 0.24 pi. So in this expression, replace s with s by omega c. You will get this expression. This is the way how to find the transfer function in Butterworth approximation method. So in this session, you learned about Butterworth approximation method, how to design analog filter transfer function using Butterworth approximation method. Thank you.